Welcome, ladies and gentlemen, to another exciting episode of Dave Does Math from Home. Today we're talking about section 15.7. This is the end of chapter 15 and the last thing we're going to do before our first test. 15.7 is about maximums and minimums in Calc 1. This was a really big deal. This was a huge part of our curriculum. We spent a while learning how to find critical points and how to identify them as maximums or minimums based on the first derivative test or the second derivative test. And then we used that information to graph things, and then we applied those techniques to story problems, and we called it optimization. We spent like an entire quarter of the class just doing max and min problems in Calc 1. It's not going to be as big in Calc 2. It's sort of just there's an extra layer of complexity to doing these problems in Calc 2 that makes we can only really do them like by hand analytically on a very small set of problems. So it's not quite as exciting as it is in Calc 1, and we're going to skip the story problem stuff so that we can get into integrals in different coordinate systems, because that's really exciting. That's where we want to be. But we do need to talk at least a little bit about optimization and how we're going to do it and what it's going to look like. Hopefully we remember from Calc 1 that critical points happen when a derivative is 0, and in some weird cases when the derivative is undefined or doesn't exist. We're going to be doing the same thing here, but getting derivatives to be 0 is a little challenging because we have lots of different kinds of derivatives. We have derivatives along x, we have derivatives along y, we have gradients. The trick is we're going to make them all equal 0. So we want the partial with respect to x and the partial with respect to y to both be 0. And it turns out if you make a gradient out of those partials at that point, if everything is 0, then the gradient will be 0. So that's the deal. We're going to make everything 0 all at once and see what kind of points we get. That's how we'll get our critical points. And similar to in Calc 1, once we had our critical points, we started testing them to see what's a max and what's a min. There's a technique for doing that here. It's called the discriminant, which is not a great name. Not a huge fan of that one, but that's the word the book uses. I'm going to be calling it H because it's originally based on Hessian matrices. So we'll use that to determine what's max and what's min. Before we start doing, never mind, I can talk about that after we start doing examples. I'm just going to start doing some examples. And I'm going to start with z equals 2x squared minus 3y squared minus 16x plus 6y equals, no, minus 10. It already equals z. Okay. Here we have a relatively tame looking quadratic in 3 dimensions. We have x squared terms, we have y terms. We don't have any mixed terms. None of the terms have x's and y's in them. So that'll be nice. And yeah, we got squared terms, we got linear terms, we got constant terms. This is a pretty regular looking quadratic. And we want to find where it has maximums and minimums. So we need derivatives. The derivative with respect to x is 4x minus 16. That's it. If we set that to 0, I think we should get x equals 4. And the derivative with respect to y is negative 6y plus 6 equals 0. And if we set, when we set that equals 0, we'll get y equals 1. So there it is. We have exactly one critical point. It's 4, 1. Except we should find a z value for this. I think the homework questions online don't really care about what these z values are. I think it's important to know what the actual z value is of this thing to determine whether it's a maximum or a minimum. Or maybe it's neither. We'll see. So here we get, when we plug in 4, we'll get 1632 minus 3 is 29 minus 64 is negative 35 plus 6 is negative 29 minus 10 is negative 39. Okay, so my critical point is 4, 1, negative 39. So now we can determine whether this thing is a maximum or a minimum or something else. And the way we do that is with the discriminant, which I'm going to call h. The discriminant in general is the second derivative of x evaluated at your point. This is a, b. If your critical point is ab, then we're evaluating this at ab. Times the second derivative with respect to y, evaluated at ab, minus the square of the mixed partial at ab. So this is basically telling us this piece will always be positive, or I guess if you're subtracting it, this back end piece will always be negative. And it only actually has a value if you have mixed terms, like x and y terms in here. So this is a measure of how many x, y terms you have and how big they are. Because when you have x, y terms, that'll complicate things. fxx and fyy, these are the partial derivatives. When you multiply those two things together, you will get a positive number if both of those things are concave up, or if both of them are concave down. So if they match in concavity, then you get positive numbers here. If they have different concavities, if one of them is concave up, like on the x-axis, it's concave up, but on the y-axis it's concave down, that's when this term is negative. So positive if they match, negative if they're different, and then you always subtract this mixed term square business. And this is to help us determine whether or not the point we have is called a saddle point. And I think that saddle point is a terrible name for these things. I think they missed a tremendous opportunity to call these things Pringles. If you think about the shape of a Pringle, like sort of on the long side it curves up and then on the short side it curves down. Right in the middle of a Pringle, we have a critical point on that surface. The derivative with respect to x is 0, because it's right at the bottom of that curve. And the derivative with respect to y is also 0, because it's right at the top of that curve. So we have this Pringle shape. Or the last time I taught this class, everyone really liked the idea of calling that a banana shape. So if you imagine a banana, like right on the, its derivative is 0 on the curve along the long side of a banana, and right in the middle. And then if you go sort of like around the banana, you're going down. You can have critical points that aren't maximums and aren't minimums if they give you these banana points or Pringle points or saddle points or whatever you want to call them. My favorite is banana points. I think I'm going to keep calling them banana points. So this discriminant, this h thing, this will help us determine whether things are banana points. This term is always going to get subtracted. So whether or not this thing is positive depends almost entirely on these second derivatives with respect to x and the second derivative with respect to y. If those concavities match, if you have positive concavity along x and positive concavity along y, that probably means that you have a minimum down there. If these things match and they're both negative, it probably means you have a maximum, because you're concave down in both your directions. Sometimes those things get screwed up if the xy terms are big enough, but we can deal with that when that happens. If the concavities don't match, if you have positive in one direction and negative in the other direction, then this term will be negative, and you're always going to subtract this term, which was always going to also be just negative. So if these don't match, you're guaranteed to be less than 0, and that's when you know for sure you have a saddle point or a banana point. So let's see what this looks like in our case. The second derivative with respect to x here, I left my marker open too long while talking. The second derivative with respect to x should be 4. I don't even have to evaluate that, that's always constant. Second derivative with respect to y should be -6. No evaluation to be done, it's just a constant. The mixed partial doesn't exist, or if it exists, it's just 0 because there's no mixed terms here. So the discriminant here, h, is always -24. And I should probably write down what the actual what we're actually doing with this. Let me write it down over here. Okay. If h is positive, then you have a max or min. If h is negative, then you have a banana point. If h equals 0, then you have not enough info. So we are in the h is less than 0 category. We are concave up along the x-axis and concave down along the y-axis everywhere. So at this point right here, we have a banana point. And it kind of makes sense that this function wouldn't have really a max or a min, because along the x-axis it's always increasing. It's never going to stop doing that. And along the y-axis it's always decreasing in both directions. And there's one point where those things sort of stop happening very briefly, but it's a banana point. So 4, 1, -39 is a banana point for us, and we're finished. That's it. We have identified all of the critical points. We have categorized them as maximums or minimums, and we're set. That's all there is. So that was a lot of me talking theory at you, sort of interspersed with some example. I think I'm going to cut the video here so that I'm not rushing to finish the next example in less than 5 minutes. But stay tuned for the next video. We've got more examples coming. We're going to investigate additional banana points. Stay tuned.